Hey, calculus students. Here are the book problems from 11-3. This is quick check number 3 and 9 through 12. So in quick check number 3, we've got 6 polar graphs, and they want us to just write or set up the integral but not solve. Well, those are common instructions for AP test questions, BT dubs. So the first one, got this cardioid, something like this, and this is the shaded region here, and that's the cardioid r equals 1 minus cosine theta. Okay, so what we need to do, we know that the integral of a polar, or the area inside a polar curve, is 1/2 times r squared d theta. That's maybe not a bad time to just remind you that it's important to write those d whatever at the end of your integrals. Don't be lazy and leave those off. They are important. And it looks like if we think polar here, so we're looking this way, comes this way, and then up here, that's at pi over 2. And come around here, that's at pi, and so on. So it looks like we need to go from pi over 2 to pi as we look at our little pi slices there. So that's that. For B, we've got, looks like a cosine circle. R equals 2 cosine theta. That's a circle with radius 1. It starts here, comes around like that, and back around like this. This tells us how far out we are at the very start, so that's the diameter of the circle. Not that that really matters. And they have this top half shaded, so that's looking from here 0, and then looking all the way till we get to pi over 2. So sometimes you can just look and it's like, well, that's first quadrant, so it's got to be 0 to pi over 2, but you have to be careful about that because sometimes things can get back to the origin before they get to pi over 2. So here we know that that is the case. And if you really wanted to convince yourself, you could set this equal to 0. 2 cosine theta is equal to 0. So I mean, that's where cosine theta equals 0, and that's at theta equals pi over 2. But I think we knew for that one. That's pretty obvious. So the integral is going to be 1/2 from 0 to pi over 2 of r squared d theta. And that's a tricky integral to solve because of the cosine squared in there. But in this case, we know that's just half of a circle with radius 1. So in this case, that'd be pi r squared, which would be pi over 2. So we can actually know that in this case. There's trig substitutions you can do, but in this case, we know it's just half a circle. C, we got a rose, and looks like I'm going to try to draw it in the way that it would actually happen, polar style. So something like that. And this is the rose r equals sine of 2 theta. That doesn't make a circle because of the 2 inside here. That's what makes it a rose and not just a circle. Okay, so let's think polar for a minute. They have the first petal of the rose shaded in here. So when I start making this graph starts at theta equals 0. I have this is 0, and then it goes out. That's like the first bump of the sine curve coming out to its peak here at pi over 2, and then it comes back here at comes back to 0, let's see, at, that doesn't make any sense, hold on a second. Oh, because it's 2 theta, sorry. So I don't get back to here until, and this is important for setting up this integral, isn't it? This is why we have to think polar. To get all the way back to here, it doesn't get back to here until the input of the function is equal to pi. So 2 theta equals pi. That means theta is equal to pi over 2. Again, you can look and kind of see that that's first quadrant stuff here, but you want to be careful. Let's check that. So 0 to pi over 2, 1/2 of r squared d theta. Okay. For d, got a spiral. This is just the regular old spiral. R equals theta. So that starts out a radius of 0, and by the time I get around to pi over 2, it's equal to pi over 2, and then by the time I get around to pi, it's equal to pi, and then by the time I get around here, 3 pi over 2, and then 2 pi, and they've got the whole thing shaded, so that's all the way from 0 to 2 pi. So that's going to be 1/2 integral from 0 to 2 pi of r squared d theta. That would be very easy to evaluate. But we're not going to do it, because they're just asking us to set them up. We've got another cardioid. This is the cardioid. R equals sine theta. So, r equals 1 minus sine theta. So let's think about what that's equal to. So when I plug in 0 into this, I would get 1. So it starts here. And then as I plug in sine values, I get these things until I get to pi over 2. The sine of pi over 2 is 1, so that gets back to the origin there. Right? And then after that, after we get to 0, then I start getting negative values. So when I look over this way, let's make a little table here to understand this better, so I'm not going to confuse myself or you. So let's see. When I plug in 0, I get 1. When I plug in pi over 2, the sine of pi over 2 is 0. Oh, I don't go back to negatives yet, do I? I get 0. And then when I plug in the second quadrant values for the sine function, I get positive things again. So that's going to give me those. It's going to repeat itself. And then 1 minus, when the sine values go negative, that's when I start getting bigger positive numbers. That's when I get all this stuff. So to get all this, it's like I need the first quadrant part and the fourth quadrant part. But I can't go, if I want to go 0 to pi over 2, then I need also this part from 3 pi over 2 to 2 pi. You could split it up into 2 integrals, or probably better, you could go from negative pi over 2 to positive pi over 2. So that's going to be 1/2 times the integral, negative pi over 2 to positive pi over 2 of r squared d theta. So fourth and first quadrants. For F, got another pretty flower. This is r equals cosine 2 theta. So let's just think polar for a minute and try to figure out what's going on here. When I plug in 0, I would get 1. And then as I go from 0 to, when I get to pi over 2, plugging in pi over 2 here, that's the cosine of pi, which is negative 1. So by the time I get to here, I'm looking at, I'm at negative 1. When when I look up this way and plug in pi over 2, I get the cosine of pi, which is -1. So how did we get from there to there? That's this part of the flower, right? And here, halfway in between, the cosine, if I plug in pi over 4, when I look this way, the cosine of 2 times pi over 4 is the cosine of pi over 2, which is 0. So that's how I'm getting back to 0 and then into those negative values. So that's all. If this was shaded here, that would be the area from 0 to pi over 2. So that's one of those kind of tricky ones where the pi over 2, from pi over 4 to pi over 2, I get negative values, so that was down here. But that's not what they want. They want, I'm going to keep just graph the whole thing, so graphs like this. So notice that this bottom half of that first petal here, that was the very last bit that I got here. So if I want this and this, that's the 0 to pi over 4, and then also the 0 back to negative pi over 4. So to get the whole thing, I need to go from negative pi over 4 to positive pi over 4 of r squared d theta. So those are a few examples with just one polar curve. And the next problems, 9 through 12, we've got 2 curves together. So now these are the ones where we're going to have 2 different curves to deal with. First one, I've got 2 curves. R equals the square root of the cosine of 2 theta, and I've got r equals 2 cosine of theta. So they gave us a graph, but let's make sure we know which curve is which. So this is just a cosine circle, right? We start out 2 units from the origin and come around this way. By the time I get to pi over 2, I'm here, and then pi over 2 to pi makes this part. So this whole area, the top half of that circle, is from 0 to pi. Now this inside, this little sort of teardrop shape on the inside, that must be this curve. And this has a 2 theta, so we need to be real careful that we understand what's happening to get back to the origin here. So when's that going to be equal to 0? Well, cosine of 2 theta, that's going to be equal to 0 when this is equal to pi over 2, when 2 theta is equal to pi over 2, and that happens when theta is equal to pi over 4. So this inside shape is from 0 to pi over 4. So if I want this shaded area, I need to do this minus this, and the limits of integration are not the same, right, because of the 2 theta there. So the outside one is 1/2 from 0 to pi over 2 of 2 cosine theta squared d theta minus that little inside teardrop thing, which is 1/2, and this one's only 0 to pi over 4. It looks like it's the first quadrant piece, but the angles are getting doubled in here, so be very careful there. That got it back to the origin twice as fast as the cosine function would. So let's see then, that's r squared d theta. So that's the setup for that, and that's as much as I would like you to do for that. Just get it set up. You can check to see if it matches up to the answer in the back of the book by evaluating that with your calculator and comparing. Number 10, got 2 curves. R equals 1 plus cosine theta. That's a cardioid, and we're just interested here in the top half of it. The other half would be like that. And on the inside, I've got r equals cosine theta. That's a cosine circle with a radius of 1/2. So this is another one that's just the outside area minus the inside area. So the outside area for this cardioid, I'm going from theta equals 0 past pi over 2 all the way back to 0 again. And you could check just to make sure you know, where does this equal 0? That's when cosine theta is equal to -1, and that's at theta equals pi. So I've got 1/2 from 0 to pi of r squared d theta, and then minus the inside part. That part of this circle happens in the first quadrant. This is from 0 to pi over 2, and then the other half would be from pi over 2 to pi. So notice again, that's different limits of integration. So I cannot combine those two integrals into one because those are different. That's cosine theta squared d theta. That's the setup for that one. Number 11, now I've got an intersection of two, and the two curves like two circles. It's r equals 4 cosine theta, so that's a cosine circle with a radius of 2, and r equals 4 square roots of 3 times the sine of theta. That's a sine circle with a radius of 2 square root 3. So let's see if we can make some kind of reasonable sketch of that. So here, there's my cosine circle with a radius of 2. So that'd be 1, 2, 3, 4. And then on this axis, I've got a much bigger, well, not much bigger, but a sine circle that would start here and go around something like that. And they want this little piece here. Okay, so really have to think polar here. This area here, let's see if I have enough room here. I'm going to blow up what's going on here. So here's that circle, and then here's the big circle. So as I start finding the area here, as I start out, it's just all area that's inside this, the bigger circle, until I get to this theta value. And from there, the rest of the way through, it's little slices that are defined by this circle. So somewhere it's going to trade off from what I have here is 1/2 times the integral inside the smaller circle for cosine theta squared d theta, and that's from 0 to something wherever they intersect. And then I'm going to add, I need to add in the rest of it from that same angle here up to pi over 2 when that gets back to here, right? That's 0, pi over 2, and then back to pi again. So I just need to find, sorry, can't multitask. I just need to find where they intersect. So to find the intersection, just like always, I'm going to set them equal to each other. So 4 cosine theta is equal to 4 root 3 sine theta. 4's cancel, and if I divide this over here, that gives me tangent theta is equal to, and then divide that over here is equal to 1 over the square root of 3. And that happens at theta is equal to pi over 6. if you feel like your unit circle trig, like to get from here to here, is very hard for you, you got to shake those cobwebs out for sure. We need to be able to do that. The nice values of the tangent function, let's see, make a quick table here, theta and tangent theta. Tangent of 0 is 0. This is sine over cosine, right? Sine theta over cosine theta. So for the other nice angles, pi over 6, you'd have 1/2 over the square root of 3 over 2, and the over 2's cancel out, so that's where you get that. And then at pi over 4, both angles have, both sine and cosine have a value of pi over 2, so pi over 2 over pi over 2 would be 1. And then at pi over 3, what we had here, they switch places. This is the square root of 3 over 2, and this is 1/2. How about the tangent of pi over 2? What's that equal to? Pause. That's undefined because you get 1 over 0, so it actually approaches a vertical asymptote here as you come up this way. Right? All right, so that's a little bit more tricky-like. Let's see if I can fit the last one over here on the same sheet. So what do we have here? Area defined by two curves again. This time I've got a circle over here and a cardioid. That looks something like this. And I want to find this whole area. This is one of those things that you could recognize by symmetry. You could find this area here and double it. And I think that that's what I will do. Or you could just go from negative angle to positive angle and find it that way. All right, so let's think polar here. Let's make sure we understand which one is which. This is a cosine circle, cosine of 3 pi. And the cardioid here, this is r equals 1 plus cosine theta. Okay? So as I go through and find my areas, looks like for a while it's just defined by the cardioid from 0 all the way up to this angle right here. It's defined it's defined completely by this cardioid. And then for the last bit, as I go from whatever this angle is to pi over 2, the rest of the first quadrant, then I'm just inside the circle. So this one is very much like number 11. I need to go 1/2 the area inside the circle, and that's from 0 to wherever they intersect, plus 1/2 from wherever they intersect to pi over 2. That's inside the cardioid. Oh, did I get them backwards? Sorry, I did that backwards. This is inside the cardioid. Here. You're probably screaming at your computer there. Sorry about that. And then this is the circle, cosine 3 pi squared d theta. And where do they intersect? I mean, if it's a nice angle, it looks like it's bigger than pi over 4, so maybe it's pi over 3, but we better figure that out for sure. So to find the intersection, I set them equal. Oops, that's not cosine 3 theta, it's 3 cosine theta. Geez, you were really screaming at the computer, weren't you? So let's see, there's 3 cosine thetas minus a cosine theta is 2 cosine thetas. So we're looking for the angle where cosine theta equals 1/2, and sure enough, that's at pi over 3. So there you go. Sorry about the scribblies. Oh, and that's just the area of this, right? And I want the area of the whole thing, so I would have to double that. how would you do it if you weren't going to double it? That would be kind of tricky because you still have to break that up into two. So I think that's definitely the best way to do it there, I think. Otherwise, you'd have to have, you could do the area inside the cardioid as one integral from negative pi over 3 to pi over 3, but then you'd have to add on these two bits as two separate integrals. There's no way to deal with that in one integral. So I like that version of it. All right, that's it.